This is the part 2 of our lecture on Gauss law. We are going to stick to our learning outcome. The first part focused on the concept of electric flux, and the second part is going to focus on the Gauss law and its application, how to apply it to solve problems. Then finally, we are going to state magnetic field, the Gauss law for magnetic field. Gauss law applies to closed surfaces only. Imagine a sphere with a curved surface like this. We can divide the surface into several small flat surfaces. That's just as you can see. We can even divide these ones into much smaller surfaces, so that each surface will become like a plane surface. Then assume also that this sphere contains a charge. If it has a charge, then the electric field around the charge will be emerging out of the sphere. If the electric field is emerging out of the surface of the sphere, then we can take the flux for each small surface. Then the next step could be to add all the small fluxes that we've calculated. If we add all the small fluxes that we've calculated for this sphere, then Gauss law is telling us that it will be the same as taking the charge enclosed within the sphere and dividing it by the permittivity of the medium. Every medium has a property called the permittivity, and we are almost always going to do the permittivity for free space. So we are going to assume that the charge will be in free space. Mathematically, this is how Gauss law is represented. Yes, we are going to explain each small feature of the mathematical equation. The first part is the small area of the surface. Indeed, we are using the sphere, but it can be any closed surface. It can be a cube, it can be any closed surface. So we take the small surface, small parts of the surface, then we multiply by the electric field strength. This together will give us a small flux. The small area multiplied by the electric field. These together will give us the small or the differential flux. Alright. Then we can do the same for every small area. So every small area multiplied by the field, small area multiplied by the field. And this sign here, the integral sign, says that we should add all the small fluxes that we've calculated. You see, so we do the fluxes, we calculate all the fluxes and make them ready. And this sign is telling us that we should sum up all the small fluxes that we've calculated. Then the circle here is telling us that we should sum all the fluxes until we've done so for all the small surfaces for a closed surface. You see, we've divided a closed surface into small area, and for each area we calculate the flux for it. Now we are going to add all the fluxes until we've done so for the closed surface. And if we add everything up, it should be equal to just taking the charge itself and dividing it by the permittivity of the medium that the charge occupies. So that's all about Gauss law. In words, the net flux through any closed surface surrounding a point charge Q is given by the charge enclosed in the surface divided by epsilon naught. This letter is a Greek letter called epsilon. Epsilon naught means the permittivity of free space. That's a vacuum. This is the permittivity of a vacuum. The property called permittivity of a medium. Okay. So, I've restated it again. So it's simply the sum up of all the small fluxes until you've done so for all the surfaces, and it will be equal to, it will be just like taking the charge itself and dividing it by the permittivity of its free space. Now, if you remember also that if we multiply the electric field by the area, we get flux. And since the area, we are talking about the infinitesimal area, a very small area, we will also be talking about small flux that will be calculated. If we add up all the fluxes for all the surfaces, then we are going to get a value that is equal to the charge within the closed surface divided by the permittivity of free space. So let's see if we can apply Gauss law and make sense of what we are talking about. Our first example, 3 small spheres are placed in free space. The spheres carry charges of Q1, the value is given, Q2, the value is given, and Q3, the value is also given. Determine the electric flux through each of the closed surfaces. So here we have Q1, Q2, and Q3. They are distributed here. We have closed surfaces drawn around them. Indeed, you are seeing the closed surface as lines, but the actual surfaces that's closer, like a bottle or like a rubber, that's wrapping around the charges. Okay, so we are going to apply Gauss law to find the fluxes going through the surfaces. Let's take the first surface, the S1. This is S1. It's in pink color. This is S1. Okay. And it encloses charge Q1, which is 4 nanocoulomb. 4 nanocoulomb. From Gauss law, we know that the total flux through the surface S1 is simply equal to the charge enclosed within the surface divided by the epsilon naught. What is the charge enclosed within S1? So if you draw S1, it will just enclose charge Q1. We put that charge there and divide it through by the epsilon naught. This is a value you should keep in mind. We'll be using it again and again and again. So it is 8.85 times 10 to the power negative 12. Keep this value in mind. If you do the calculation, you are going to get 452 Newton meter square per coulomb. Just check it out. So the flux through the surface S1 is 452 Newton meters per coulomb. I will leave the second one for you to do because it's the same thing. Just that the charge enclosed is negative 7.80 nanocoulomb. So if the surface 2 encloses only charge Q2, then what will be the charge enclosed divided by the epsilon? Epsilon, the value I've given it to you in the first calculation for the S1. Just use it, and I expect you to get 881 Newton meter square per coulomb. Let me assist you to do one more. Calculate for the electric flux through the third surface, which is S3. Now let's trace S3. S3 will be the green surface, and let's see, it goes through here all the way through that side to the other end. And we can see clearly that it encloses Q1 and Q2. So the total charge enclosed within the surface S3 is Q1 plus Q2, which is 4 plus negative 7.80, which is the same as 4 minus 7.80. If we do this arithmetic, we are going to get something like 3 point something by 10 to the power negative 9 coulomb. It is nanocoulomb. So it's going to be 3.8. Sorry, it's 3.8 here. And if you do the calculation, if it is not exactly this value, then it will be something around this. So try it yourself. I'm sorry for that. But the correct thing is that we have to sum up all the charges within the surface. We have 4, positive 4, then we have negative 7.8. We sum them up algebraically and we get negative 3, yes, we get negative 3.8 times 10 to the power negative 9, and we are going to get something around this. Try it yourself and let's discuss. You can continue and do for surface S4 and S5. S4 is the mauve one, violet or purple color. It encloses Q1 and Q3. So the charge enclosed will be the sum of Q1 and Q3. Similarly for S5, it encloses all the 3 charges. You just have to add up algebraically. If it is negative, negative. If it's positive, positive, then you divide by epsilon naught and you get the flux through the surface S5. Let's take a second example. A point charge Q1 has a charge of 4.00 nanocoulomb and is located on the x-axis at x equals 2.00 meters. And a second point charge Q2 with that is also located on y-axis at a point y equals 1.00 meters. What is the total electric flux due to these 2 point charges through a spherical surface centered at the origin and the radius? Very often, it's proper to get a mind picture of what is actually on the ground, and this is what we have. One charge, which is Q2, is located on the y-axis, and Q1 is located on the x-axis. This one is 2 centimeters away from the origin, and the Q2 1 meter away from the origin. Now, this is our first sphere. That sphere has a radius of 0.5 meters, so just half of one big box. What will be the flux through this one? There is no charge. The charge enclosed in this sphere is 0. So the flux through the surface will also be 0. As simple as that. Because whatever the value on top here, if we divide by any value, however big it is, it will give a 0. Let's go to the second one. The second one has a radius of 1.5. This is the second sphere that we've drawn, and it is centered at the origin with a radius of 1.5. This is from here to here is 1 meter. From here to here is 0.5 meters. So we draw this one and we realize that it encloses only one charge, which is the Q2, 6 nanocoulomb. So what will be the flux on the surface of the sphere? Again, from Gauss law, it will simply be the charge enclosed divided by the epsilon naught, and the charge enclosed is 6 nanocoulomb. Straight away. Let's move to the third one. The third sphere will be 2.5 meters, centered at the origin, and it will be this large sphere containing the 2 charges. So we just have to sum up the 2 charges, getting 10. 4 plus 6 gives us 10, and we go through the routine. That's so simple. Now let's do the last one. A point charge Q1 equals 6 microcoulomb is located at the center of a cube. Determine the flux in one surface of the cube, in just one surface of the cube. So we have a cube, as we saw in the first lecture, and there is a charge at the center. So the cube has 6 surfaces. We are expected to calculate the flux through just one surface. So this is how I went about it. According to Gauss, the total flux over the closed cubic surface is equal to the total charge enclosed divided by epsilon naught. So what was the charge enclosed? It says microcoulomb. Micro is -6. So we divide that one by the epsilon naught, which is 8.85 times 10 to the power negative 12, and we get this. This one is for the total flux across all the 6 surfaces. So if we need the flux across just one surface, then we simply have to divide by 6. That's alright, so we divide by 6 here, 1 divided by 6 multiplied by the total flux, we get 1.12 by 10 to the power 5 volts meter. So this will be the flux through just one surface. So if we add up this 6 times, then we are going to get the total flux. Okay, that's it for now.